Okay, hello and welcome to your first video lecture. Sorry if this is a little bit rough. I am still figuring out some of the technology that is needed to make these videos, but I appreciate your patience. Hopefully this goes smoothly and the future ones will go even better. So today we're going to talk about decision trees. And decision trees are a way that we use an algorithm to classify data into different categories. So this is similar to how we were doing logistic regression, where we took predictors, both continuous and categorical, and we used them to predict the category of another variable that is the thing that we're trying to guess. So just FYI, in terms of where we are, you can see we're predicting a category. There are different types of trees called regression trees where you can predict a continuous output, but we won't be talking about those today. Okay, so decision trees are essentially a tree structure, which is what you hopefully see in front of you. You might see this as kind of like a flow chart where you start somewhere and then you go boop, 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 and you make a decision eventually, hopefully. So a decision tree is essentially one of these flow charts that we make with math. And what we're going to do is we are going to have a bunch of different decisions based on variables in our data set, and eventually, hopefully, that will lead us to different categories. So if you've ever played the game 20 Questions, then you might be familiar with this sort of decision tree type structure. So say I'm thinking of something, I'm thinking of a skunk, and someone is playing 20 questions with me. So they're trying to guess the thing that I am thinking of, which is a skunk, and they get to ask up to 20 questions. Well, the first thing that this person might ask is the thing you're thinking of alive? And you can either have yes or you can have no. And in my case, I would say, yes, the thing I'm thinking of is alive. So once they know it's alive, they might say, is it human? And that could either be yes or that could be no. And I would say, no, it is not human. So then we're here. And the question after that would be, well, maybe is it something that people keep as a pet? So it's a pet. And you can either have yes or you can have no. And in this case, I would say no, because hopefully most of you are not keeping a skunk as a pet. So you can see that this type of decision tree structure is something that we hopefully are a little bit familiar with. You may even subconsciously use it in your day-to-day life. For example, if you have a break between classes, you might use some sort of decision tree-like structure in order to decide what you're going to do with that break. So for instance, you can say, okay, I have a 20-minute break. What am I going to do? Well, my first question might be, do I have any homework due? If I do have homework due, then I would say, well, do homework. If I don't have homework due, then I might say, am I hungry? If I am hungry, then my decision might be to eat. If I am not hungry, then my decision might be to read a book. So you can see that we use these types of decision tree structures in our everyday life. Now, we're going to build one with math. So think of this question, I suppose. Say we have a data set and we have the outcome or the output that we want to predict whether or not something is a bird. And the data that we have is yes, no, can this thing or animal hopefully fly? Well, we can use this to make a decision tree, and actually a decision tree that has only one layer of nodes is called a decision stump, which I think is kind of funny. Anyway, So you can have this decision tree where if something, the animal that we're looking at from our data set, can fly, then we will classify it as a bird. If it can't fly, then we will classify it as not a bird. Now, this is not perfect, right? We all know that there are some birds that can't fly, like an emu, I believe, and a penguin. But also there are things that can fly that are not birds, for instance, a bumblebee. So it's not perfect, but this does an okay job at helping us classify whether things in our data set are birds or not birds. But we can also have more complicated tree structures. So let's say we're not super happy with just deciding if something can fly, we'll classify it as a bird. So instead of saying when something is not a bird, that it is, or excuse me, when something cannot fly, that it is not a bird, we'll instead now ask, does it have feathers? If it does have feathers, even though it can't fly, we will still classify it as a bird. If it does not have feathers, we will classify it as not a bird. So you can see that we have a slightly more complicated structure. We no longer, like we did above, just have two or like one layer with two output nodes, and it's just yes, it's a bird, or no, it's not a bird. Now we have a slightly more complicated decision tree structure, and it's no longer a decision stump. So while we're here looking at this more complex tree structure, let's just go over some vocabulary that we're going to use. So when we have a tree, what we're going to mostly be talking about is things like the node. And the node is the topmost part of the tree where you start. So when you're looking at whether we're going to classify things as birds or not, you start here at whether or not it can fly. So this is the root or the root node. Once you have a classification like this, this, or this, these are called leaves. And so a leaf node is essentially the end of that path on the tree. It's where we decide to put something in a category or not. So in the decision tree world, you can use both categorical and continuous data in your tree. We'll talk a little bit about how to do that in a second, but I just want to point out for now that our our decision tree is taking predictors, and these can be either categorical or continuous. And it's using that to build a tree that is predicting some type of categorical, some kind of categorical outcome. So you can see on this page a little bit that you can have, can it fly? Yes or no. We can also use continuous variables. For instance, in this tree on the right, you can see that I'm using age to decide whether or not someone plays Fortnite. And my decision is if they're less than 20, then I'm going to assume they play Fortnite. And if they're more than 20, then I'm going to assume that they do not play Fortnite. Okay, so as I said before, we're going to build our decision trees with math. So let's go ahead and do some math. So in this data set that we're looking at, actually, let me go back to this. We are predicting, as I mentioned in class all the time, we're predicting whether or not someone has a cat. Now, we have a couple different variables that we can use in order to make this tree or make this prediction in general. So the first one we have here is whether or not someone had a childhood pet. So 1 is yes, 0 is no. We have their income in thousands of dollars. We have a yes-no variable, whether or not they work from home. 1 is yes, they do. 0 is no, they do not. And then here we have whether or not this person has children. So it's going to be 1 for yes, they do have children, and 0 for no, they do not. Now, how do we decide what is going to be the root node of our tree? Well, we do it with math, and the way that we do it is we look at each variable. For now, I'm going to ignore income. I'm only going to look at the categorical variables. But what we do is we essentially try out each variable and see how well it does. So let's start with work from home. So if work from home is our root node, then we can have two branches. We can have yes, they work from home, or no, they do not work from home. And when they work from home, we end up getting 4 cat people and 1 non-cat person. And you can see that, I'll color code it. So when you look at work from home, you have boop, this one, this one, this one, this one, and this one. And out of all of those, 4 of them own cats and 1 of them does not own a cat. So you can see that here. And then when we look at people who do not work from home, all of these, you can see that we end up with, let's put cat, no cat. We end up with 2 people who own cats and 3 people who do not own cats. So you can see that using work from home alone is not perfect, because no matter how we categorize these, you can see that in the left-hand node over here in red, we have in this node people who both own cats and do not own cats. Now, it's mostly people that own cats, and in the right-hand node in orange, you can see that it's mostly people, well, almost, who don't own cats. So it's doing okay, but it's not perfect. And when we have these mixed results where we have in one node people who are in more than one category, we call that impurity. And the way we're going to mathematically represent impurity or measure impurity is with this formula up here, which is called the Gini. Oops, didn't want to circle there. This is called the Gini Impurity. So this is a score that is going to tell us essentially how well the nodes split things into the correct categories. And you can see that it's going to be 1 minus the sum of the probability of each category squared. So let me show you what I mean. I'll switch back to red. So for this left-hand node here, the Gini impurity is going to be 1 minus the probability of one category. So let's look at just cat owners. So we can say 1 minus the probability of being a cat owner given that you're in this node. So that's 4 out of 5 squared minus 1 out of 5 squared. And remember, the place that I'm getting these 4 out of 5 and 1 out of 5 is 4 out of the 5 people in this node own a cat, and 1 out of 5. And these people, 1 out of 5 of these people in this node do not own a cat. So when we get that all together and we do the math, we get that the impurity for this part of the node is 0.32. So I'm just going to circle that. Now, let's do the other one. Well, we have 1 minus, and then the probability of being a cat person is 2 out of 5 squared minus 3 out of 5 squared. And when we do this math, we get that the impurity here is 0.48. Now, we are going to take these and average them together, because what we want to know is, did this split here, up here that we just made, what is the impurity of that? So what we're going to do is we're going to take a weighted average of these two scores, 32 and 48. So we're going to say how many of our data points are in the left-hand node. Well, it's 5 out of a possible 10 times the impurity for that node, which here is 0.32. And then we're going to add how many are in the right-hand node, 5 over 10, and times the impurity for that node, which is 0.48. So this is what we call a weighted average, and when you look at it all together, you get an average impurity of 0.4. So when we split on work from home, we can see that the impurity is 0.4. Let's try, section this off here. Let's try with a different variable. Let's try, I'm going to need one bigger than that. Let's try whether or not someone has a child. So we'll go children. So in our data set, we have people who have children and who do not have children. And when we split by that, we get in the children category. Let's get some colors. I'll do dark green. People with children are here, 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 and here. And when we look at that, we can see that for cat people, we get 3 cat people. For no cat people, we get 4. And then let's pick this color blue. So for people who do not have children, here, here, and here, we get for cat people 3, and for non-cat people 0. So let's calculate the Gini impurity for this split. Well, I'll start over here because the math's a little easier. So remember, the Gini impurity is 1 minus the probability of being in one category. So here that's 3 over 3 squared minus the probability of the other category, 0 over 3 squared. And you can see the math works out a little bit nicely here because we have a Gini impurity of 0. Now notice that a Gini impurity of 0 happens when a node has only one category in it. So in this node, people who do not have children, at least in this data set, there are only cat people in that node. And remember, we want to reduce impurity. The ideal situation would be that we would perfectly classify people by the end of our tree. And so it makes sense that impurity is low when we have all of one category in one node. However, we also have another node. So let's calculate the impurity here. It's going to be 1 minus the probability of being a cat person, which here is 3 over 7 squared, minus the probability of not being a cat person, 4 over 7 squared. And when we do that math, we get an impurity of 0.49. So now, as before, we need to create a weighted average of these two. And on the left-hand side, we have 7 out of 10 of the variables, or the data points, times the impurity for that node, which is 0.49, plus how many are in the other one? 3 out of 10 times the impurity for that node, which is 0. So this just goes away, and all we have is 7 over 10 times 0.49, which, if we do the math, equals 0.343. Now, I won't make you sit through the other one. The other variable that we have is childhood pets. I'm just going to tell you, childhood pets, that the impurity here is also 0.4. So again, right now we're ignoring income, so we only are looking at the 3 variables. Do they have children? Do they work from home? And do they have a childhood pet? And what we're going to do is we're going to say, okay, we looked at what would happen if the root node was each of these variables. Which one had the lowest impurity? So at every step that we're making at the at the decision tree level, every decision we're making, we're going to choose the option that gives us the lowest impurity. So in this case, we are going to start our tree with, do you have children or not? Because that had the lowest impurity of all of the 3 options that we looked at. Okay, so we can also do trees with continuous variables. The math is a little bit longer. It's not harder. It's just more things to check. So what we're going to do is we're going to look at income now, which is our only continuous variable. And what we're going to do is put in order every data point from least to most. So you can see from least income to most income down here. Now I'm working with a slightly smaller data set just because, as you'll see in a moment, this is a lot of math. But the principle still holds even if we have 1,000,000 data points. So what we're going to do is we're going to say, okay, of these data points, one place that I could draw my decision boundary is between these 2 points, the red line that I just drew. And what we're going to do is we're going to say, okay, if this was our line, what would the impurity be? So when we look at this, we're essentially saying income is either greater than about like 59, we'll say 60,000, or not. So if it is, then we have these 3 points at the bottom. And so for those, we have 1 CAP person and 2 non-CAP people. For people whose income is not below that, we have 0 CAP people and 1 non-CAP person. And so when we when we calculate the impurity here, we're going to get 1 minus 1 over 3 squared minus 2 over 3 squared. And remember, I'm getting those numbers from here, from the probability of being in the CAT category for this node and the probability of being in the no CAT category for this node. And then the impurity over here is going to be 1 minus 0 over 1 squared minus 1 over 1 squared. And we can see here that the impurity for this part is just 0. So when we create a weighted average, which I should probably do that calculation. So this is 0.44. We have to create a weighted average, which is going to be 1 over 4 times 0 plus 3 over 4 times, didn't want to do that, times 0.44. And when we do this all together, we get an impurity of 0.33. Now, that's not the only place that we could draw our decision boundary. We could also draw it here where the orange line is. Now, if we draw it here, then we're essentially saying the root node of our tree is income greater than or equal to about 75K. If it is, then we're talking about these 2 data points down here, and we have 1 CAP person and 1 non-CAP person. So we'll put yes here. For the no people, we have these 2 up here, and we have 0 CAP people and 2 no CAP people. To create the impurity, we're going to say 1 minus 1 over 1 squared minus, 1 over 2 squared minus 1 over 2 squared. And again, this is the probability of being in the CAT category for this node. This is the probability of being in the non-CAT category for this node. And this is going to be 0.5, which hopefully makes sense because you can see that there's an equal number of CAT and non-CAT people in here. So obviously this didn't do a very good job of classifying people as either CAT or no CAT. On this side, we're going to have 1 minus 0 over 2 squared minus 2 over 2 squared, and our impurity is going to be 0. And remember, impurity is 0 when we have all of one group in that node. So one node that only has one category in it. Now we need to create a weighted average. So we're going to do 2 out of 4 times 0.5 because 2 out of our 4 data points are in that node that has 0.5 impurity. Plus, let's put some parentheses there, 2 out of 4 times 0, which that's just going to be 0. And so for this split, we end up with an impurity of 0.25. Now, this is not the only place that we could draw our line. The last place that we could draw our decision boundary is right here where this green line is. This is essentially the same as creating a root node. Let me do something darker so you can see. This is saying the same as creating a root node and saying is income greater than or equal to $76,000. Well, if it is, then we only have one data point down here, and we have 0 CAT people and 1 no CAT person. If their income is not above 76,000, so these 3 people at the top here, then we end up having 2 CAT people and 1 no CAT person. So let's calculate the impurity. Well, look, we see over here that there's only one category that's represented in this node. So we already know the impurity here is 0. In this node, we have 1 minus 2 over 3 squared minus 1 over 3 squared, and that's going to be equal to 0.44. And again, we've got to create a weighted average, so we're going to have 3 over 4 times 0.44 plus 1 over 4 times 0, which that's just 0, and we end up with an overall impurity of 0.33. So you can see that with a continuous variable, you still get these different Gini impurities, and your job is to choose the lowest one. So in this case, we would say we want to create our decision boundary here. Not there. We want to create our decision boundary, where did I put it? Here. Because 0.25 is the lowest impurity, so that means this orange line here is the cutoff that we would want to choose for that continuous variable. So, in essence, the way that we build our tree structure is we make a split, whether on a categorical variable by the category, or if it's a continuous variable, we look at each possible split we could make. And we calculate the Gini impurity for it for each node. Now, we did Gini impurity. There's actually multiple ways to calculate how well a decision or a split classifies a category. The other way is something called information gain or entropy. And when you see how we build these models in sklearn, you'll be able to see that you're able to choose which one you want your decision tree to use. And just remember, entropy is essentially a measure of chaos and disorder. I actually have a funny story. So when I was a kid, one time my mom came up to my room and was really upset that my room was not clean. And she asked me why it was so messy. And I looked at her and I said, entropy. My mom did not like that. She ended up saying, it's not entropy, it's entro-Chelsea. She thought she was very clever. But essentially, this story is just a silly way to illustrate to you that entropy is a measure of disorganization or chaos. And so you think, okay, well, if a node has a lot of chaos, that probably means that it's not very good at classifying the thing that I want it to classify. So in the same way that we use impurity, we can also use entropy or information gain in order to decide which node is the best. So once you've calculated, we'll go with impurity for now. You're going to choose the node or the method of creating nodes that had the lowest score, because we want impurity to be as low as possible. So I'll go over the last step right now. So as you can see right now, we've only been creating essentially decision stumps because we've only been doing one layer of our decision tree. Well, we don't have to stop there. So if you remember, I'll scroll up. If you remember when we were looking at our 3 categorical variables, we decided that children was the best of our categorical variables to start with. It had the lowest impurity of all 3 choices. So let's start with that tree. So we have up here children. And we have, yes, they have children. No, they do not have children. And so in this node right now, what we have is, okay, let's scroll up and find it. Okay, so we had cat people. We had 3 cat people and 4 no cat people. And then here we have 3 cat people and 0 no cat people. So this is where we're at right now. Now, what we're going to do is we are going to look at, okay, well, can we improve this decision by adding another layer to our decision tree? Now, I'm just wanting to point out here, I picked this example for a reason. If you look at this node on the right here, there's really no way that we can improve this node, right? The impurity here, you'll say impurity is already 0, and we can't get an impurity that is lower than 0. So I'm going to leave this node alone. There's no possible way I can improve it. The only thing I could possibly do is make it worse. So we're not going to add anything there, because why would I want to make it worse? But on the right-hand side, we actually can improve it here. So let's look different color. Let's look here. So instead of just classifying everyone in this node as, for example, no cats, what we can do is use one of our other variables in order to further break down the classification. So what if here, let's make this a little bigger for a second. What if instead of just classifying these people as you don't have a cat, we said, let's look at their work from home. So just for these people who said they do have children, let's look at whether or not they work from home. So that's too big. So what we're going to do is we're going to say for this group of people, so only the people with children, how many of them work from home? And I should have copied this down here, but I have it up here. So we have, actually, let me grab that so that we can have it down here. Boop. Okay, we'll copy. Hopefully that copied everything. Paste image. Okay, so, I want that a little bit over here. Come on. Okay, well, it wants to go there. So what we're going to do is we're only going to look at people who do have children. So let's look at that. Okay, so this person has a child. 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 And these 3 people have a child. So we're only looking at the rows that I just highlighted here. And out of these people, you can see that we have, for people who work from home, we have 3 of them total, and 2 of them have cats, and 1 of them has no cat. For people who have children and do not work from home, we have 1 person who has a cat, and 3 people who do not have a cat. So let's look and calculate the Gini impurity for this. So we have 1 minus 2 over 3 squared minus 1 over 3 squared, and that's going to be equal to 0.44. And then over here, we have 1 minus 1 over 4 squared minus 3 over 4 squared, and that is going to be equal to 0.375. Now we need to calculate the weighted average of these. So we're going to say in the left-hand node, we have 3 of our 7 people, and that is going to be times the impurity for that node, which is 0.44, plus how many are in the other node? 4 out of 7 are in the right-hand node. Oh, didn't want that yet. Times the impurity for that node, which is 0.37. Oops. Didn't want that. Okay, 0.375. So when we do all of that math, we're going to end up with a weighted average of 0.40, about 3. Okay, so essentially we can see that this node, when we split it by work from home or not, has an impurity of 0.403. Now, in order to make a decision, we would have to calculate what it would be like if we did childhood pet, the other category as well. And I'm not going to make you sit through the math, but I will put here that childhood pet, so if we replace this work from home node with childhood pet, we would end up with an impurity of 0. What is it? I think it's 0.49, something like that. Okay, so we have essentially 3 options. We have childhood pet here, which will end up with an impurity of 0.49. We have, let's change color. We have 0.43, which is, or 0.403, excuse me, which is what happens when we put the work from home node there. And then what we have to do is remember that one of our options is just to leave the node alone. And we can remember from the example above, I'll scroll up to it really quick. That's continuous one. When we just leave the node alone, then we have a, sorry, you can see that here. Then we have a Gini index of, what is that? 0.49. So I'll write that down here. So if we leave node alone, so that means essentially we don't make this second split. If we leave it alone, our impurity is 0.49. So of these options, we have to choose which of those is the lowest. Well, it's 0.403. So we are going to choose this one, which is splitting on work from home. So if you scroll back up here, you can see that the basic steps are for each level of your tree that you're creating. We're going to calculate the Gini impurity, or if we end up using the entropy/information game, for each of the splits or the nodes that we make. We're going to choose the option that gives us the lowest impurity score. So essentially, which split does the best job of splitting things into the correct categories? Excuse me. And then if we're ever adding a layer, we're going to compare not only does this split do well, but does it do better than leaving the node alone? So we saw here that when you use work from home, it does improve the impurity. So we would have a tree, let me draw it out here with a little bit less mess and numbers. Our tree is going to end up being, do you have children? If yes, then do you work from home? If yes, then we're going to classify you as a cat person. If no, and I should put those here, then we'll say you're no cat. Over here, you can see that we're going to say if you don't have children, we're just going to guess that you do have a cat. So let's color code these really quick. So we have cat, cat, I'll do this color, no cat. So we've essentially just built a decision tree. We could keep doing this forever and ever until we've used all of our variables or until we have all leaf nodes. But you can see the process that we're using is we're iteratively adding layers to our tree, and we're checking to see, does adding a split on a certain variable here improve our ability to predict the right category, or does it not improve? If it doesn't improve, then we use something else. If it does improve, then we use that split. So hopefully that gave you a little bit of a better idea of how we create decision trees. In class, in our virtual class, we'll do some more examples just to make sure your math is solid. And we'll also do some coding where we use code to calculate our Gini index. You can get a little bit of a better handle on what that would look like. But what I want you to take away from this overall is that what you're doing with a decision tree is you're creating layers, and at each layer, you're saying, what is the best decision I could make at this point? You're making that decision, and eventually you end up with a beautiful tree like this that can classify people into whether they have a cat or do not have a cat. Okay, I am very grateful that you sat through this lecture. I hope that this was easy to understand and easy to see. Like I said, the technology part of these online lectures are going to get a lot better. So hang in there, it'll all be fine, and I will see you for class. Bye.